a higher level of uncertainty in general. However, they also perceive uncertainty to be more aversive. So there's a kind of joint problem whereby people seem to be more uncertain and also really don't like that uncertainty to a greater extent. And you also see that people with anxiety disorders have heightened physiological responses as well. So it's not just a psychological thing either. There's something physiological going on in terms of how people respond to anxiety, to uncertainty, that seems to be altered in some way in people with anxiety. So this was my kind of initial motivation for looking at anxiety when I kind of started my postdoc. It seemed to be so intimately linked to symptoms of anxiety that my plan was, if I could figure out how people learn about uncertainty, how people estimate uncertainty, respond to it, maybe that tell us something about anxiety disorders. It turned out to be quite complicated. I never really got that far, but hopefully along the way I've discovered some interesting things that I can talk to you about today. So one of the difficulties we have in assessing uncertainty is that we ideally want to try and recreate some of the complexity of naturalistic environments, which are often very unpredictable, and therefore, uncertainty is really key. So in more naturalistic kind of situations, it's really important that we adjust how we're behaving according to uncertainty, because there is a huge amount of uncertainty in the real world that we're living in. So one question we want to kind of ask then is, how do people keep track of this uncertainty that we're faced with in everyday life? How do we learn about that uncertainty, maintain representations of it in the brain? And this is kind of in line with some work that or some kind of writing I've been doing recently, I guess, where we've really tried to emphasize the importance of looking at how people learn about and make decisions within real world environments, encompassing all their complexity. So trying to actually kind of, rather than ignore the complexity of naturalistic environments, actually try and understand how people deal with that complexity. And for me, at least, dealing with uncertainty is a really big part of that. So the first question I'm hoping to address in this talk is, how do people actually track uncertainty during learning? And building on top of that, do people that actually kind of differ in how they track uncertainty, or is it quite a stable thing across people? However, the other thing I want to ask is how this process of uncertainty estimation is linked to anxiety. Is it the case that if we do see individual differences in how people estimate and track uncertainty, that those individual differences show some sort of relationship with symptoms of anxiety in particular? So the first study I'm going to talk about is one that I did a few years ago, looking at how learning how uncertainty and learning kind of interact, and how that also interacts with the process of visual attention. So we know, for example, that uncertainty is really important in learning. There's a lot of theoretical work indicating that maintaining estimates of uncertainty is important in guiding our learning. If we're more uncertain in general, we probably want to learn a bit faster about things that are happening to us. If we're more certain about our current understanding of the world, we probably want to learn a little bit slower and pay less attention to things that are happening. So I sought to kind of understand a little bit more about how people learn about uncertainty and how uncertainty influences learning in this study that we conducted back in 2019, which was published in PLOS Computational Biology. To do this, I wanted to create a task that actually made people feel quite uncertain, and also a task that was aversive as well, because I was interested in anxiety. Often when you're looking at anxiety, it makes sense to focus on the more aversive side of things. So to do that, I developed this kind of learning task where people have to track changing stimulus probabilities. The probability here representing the probability of you being given an electric shock. And this is not a particularly novel task design in general, but here we really try to make things fluctuate quite fast to try and really amp up the uncertainty that people are feeling within that task. So here in this example of one of the blocks of the task, we have 40 trials. We have one stimulus, which is associated with a very stable probability of shock. That's the blue one. Whereas we have this orange stimulus here, where the shock probability changes very rapidly throughout the task. So you only have, I think, sort of 7 to 10 trials where the shock probability is consistent, and it tends to move around very quickly as a result. what this means is that you have two stimuli, one of which you end up being quite certain about, the other you end up being quite certain about. So as a result, this gives us quite a nice way to increase people's uncertainty about particular stimuli while making them quite certain about other stimuli. And as I mentioned, this was done using electric shocks. So it's very aversive. People actually end up getting quite a lot of electric shocks. I think they forgave me for it. It wasn't too bad, but it did end up with quite a lot of electric shocks. Not the most enjoyable task to do, but people did tend to report that it made them feel quite anxious. So that's really helpful if we are looking at processes that we think are important with regard to anxiety disorders. So if my slides move on. What we wanted to do is take people's behavior within this task and build computational models of it, computational models that track uncertainty. By doing this, we can get a handle on how people are actually tracking that uncertainty, how they're learning about uncertainty based on the outcomes they're receiving, and how they're actually maintaining some sort of representation of that uncertainty. To do this, I turned to a class of model, which we refer to as beta learning models. The reason for this is that they represent the probability of receiving an outcome, in this case, an electric shock, using a beta distribution. Beta distributions are really nice for representing probabilities because they represent quantities that are bounded between 0 and 1. So for probabilities, that is perfect. And we can create simple computational models of learning using this basic principle. These models are really simple. They're not kind of perfect in that they don't maintain a perfectly accurate probability distribution, but they do approximate it in a way that is really useful if you want to be able to look at how people are learning about uncertainty. So just to give you a little bit of insight into how these models actually work, at their heart, they are extremely simple. They're basically just counting. They're counting the times that you get a shock, in this case, the times you don't get a shock. Equally, you could change this around for a different type of task. You could have it, probability of getting reward, anything like that. But basically, in this case, they're just counting shock and no shock. Now you can see that, I don't know if you can see my mouse. Hopefully you can see something like a mouse. But anyway, hopefully you can see here that essentially this blue line is our distribution. We've received no outcomes whatsoever so far. So our distribution is entirely flat. Everything is just as likely as everything else in this case. We're not biased towards thinking we're going to get a shock or thinking we're going to be safe. If we look at the mean and variance of that distribution, as plotted at the top using this point and the error bars, it's all in the middle. We've got a lot of variance around that kind of mean estimate because we don't really know much. We've not really received any information at all so far, so we're completely uncertain. Now, if I then receive one outcome which indicates that I've actually been safe, i.e. in the context of this task, one particular stimulus has not given me a shock, that's going to push the distribution slightly towards the left, i.e. that there's a lower probability of receiving an electric shock. So here in the blue, our probability density function becomes slightly skewed towards left a little bit. Correspondingly, the mean probability estimate goes down and the variance shrinks a little bit as well. So we're becoming slightly more certain about the fact that we're not likely to get a shock. If we then receive a shock outcome, things change a little bit. We become even more certain because we've got more evidence, but the mean estimate kind of swings a bit more towards the middle. So you can see that this distribution is getting a little bit more precise. And this continues. As we receive more and more evidence, the distribution becomes increasingly precise and will kind of converge on the appropriate kind of mean estimate of the probability as time goes on. And so you can see that this model is really simple. It's literally just counting the occurrence of different outcomes. But through that very simple process, we managed to build an approximate probability distribution over the probability of getting a particular outcome. The really nice thing about that, of course, is that because we have this distribution, we have a metric of uncertainty inherently within what we're estimating. We have the variance of that distribution. And so despite this being a very simple model, we get both the mean and the variance. We get a point estimate of the probability of getting a shock and also a measure of uncertainty around that shock probability. And you can take this further and further and further as far as you like. In reality, one thing that I should note is that the problem with this model as it is that this will keep accumulating evidence forever and ever and ever, and eventually it will become extremely certain about the average probability of getting an electric shock. if we have a task like the one I'm describing here, we don't really want that, at least for the orange stimulus here. Instead, we want that probability that we're estimating to change as time goes on, because clearly things are changing throughout the task. We want to maybe forget a little bit of what we've learned at the past, so that our estimates are kept up to date. And so what we actually do within this model is we have a decay parameter, which allows these kind of accumulated values to decay over time as well. So as well as adding to these counts, we're also letting them decay as the task goes on too, which means this model isn't kind of stuck based on what it's learned in the past. It is able to be flexible and update in response to new information that's coming in. Another nice thing about these models is that we can very straightforwardly incorporate biases in learning. So you may imagine, for example, in this type of task, people may learn at different rates about shocks or safety. So potentially people who are very anxious, maybe we might expect might learn a lot faster about shocks than safety. This is kind of analogous to learning rates within more standard kind of Pascal or Wagner style models. They work slightly differently, but it's the same basic kind of principle. And so here, for example, if we have, let's say, a very negative bias in our learning, where we're paying a lot more attention to safe, so hang on, no, very positive bias, sorry. We're paying a lot more attention to safety than we are to shocks. You can see again, we get a safe outcome, the distribution shifts to the left a little bit. But here, when we receive a shock, that doesn't really do much to that distribution, because here this person has a very kind of positive bias in their learning. They're paying a lot of attention to the safe outcomes, not very much attention to the shock outcomes. We can keep this going and we can add more and more shocks, and yet this person still thinks that most likely they're going to be safe. And you can flip this around as well, of course. So if you wanted to, you could have completely the opposite kind of bias, whereby people are paying far more attention to the shocks than the safety. And then you have this kind of pattern where people just think that they're going to get shocked all the time, even when actually they're going to be safe. So I think it's very kind of intuitive to see how this sort of bias in learning might relate to symptoms of conditions like anxiety, where people tend to have a quite persistent and kind of resistant to change view of the world as being overly negative. So this is the basic model that we used in this task. And so out of this, we get some nice parameters that we can do interesting things with. We get these kind of update rates, which determine how biased the learning process is in terms of positive and negative outcomes. We get this decay parameter that determines how quickly people forget about things. And then we also get these metrics of uncertainty that people are tracking throughout the task. These are all metrics that we can link to individual differences or other aspects of behavior. And so despite this being quite a straightforward approach, we actually get a really interesting amount of information out of it. So just to re-emphasize this, if I have a negative bias in my learning, basically what I end up doing is assuming I'm going to get shocked all the time. Vice versa, if I have a positive bias in my learning. So yeah, again, straightforward models, but they tell us some interesting things. So we did, of course, run model comparison within this kind of task to find out whether these models that we were coming up with actually did a decent job of explaining the data, and thankfully they did. We compared this kind of modeling approach. We refer to this as the asymmetric leaky beta. It's a beta model because it's a beta distribution. It's leaky because it's got this decay parameter, which means that it kind of forgets about things. And it's asymmetric because it updates at different rates for shocks and safe outcomes. But we found that this did a much better job of explaining the data than a variety of competitor models. If we take out the asymmetry, so we just have the leaky beta without any asymmetry in it, that does not do as good a job. So clearly people do seem to be learning at different rates about shocks and safe outcomes. We can use a more standard kind of reinforcement learning model that tracks and responds to uncertainty, the Pierce-Hall models. We had two different types of them. They don't do quite as good a job either. We can have models that don't respond to uncertainty and have either kind of asymmetry in their learning rates or no asymmetry, i.e. the standard Wagner and a version of that with different learning rates. They don't do as good a job either. So it really does seem like, at least within this task, people are kind of tracking uncertainty and responding to it in a way that isn't well explained by more standard reinforcement learning models. Um, it's a bit hard to say exactly why that is, but there's clearly something about these beta models that does a really good job of explaining people's behavior. I will say that there's evidence from other studies showing that models that are kind of approximately Bayesian in nature, like these ones, seem to provide a relatively good fit to data when they're kind of aversive learning tasks, but maybe not so much when they're reward learning tasks, which might suggest that there are different kind of learning mechanisms going on in those different types of scenarios. And potentially maybe that might speculatively imply that tracking uncertainty becomes more important to people when there are aversive outcomes, but that's very much speculation at this point. So now we have this model, we know that it fits the data really well, we can start to do some interesting things with it. And so we can look at whether there are actually individual differences in how people learn from positive and negative outcomes. Now, interestingly, overall, people are tending to update to a greater extent in response to danger than safety. So overall, people have a fairly negative bias in their learning. They're paying a lot more attention to danger than they are to safety. But you can see from this figure here that the distribution of those parameter values is really, really quite wide. They're almost taking up the entire range that they could possibly fit into. So we do see this overall pattern where people are more negatively biased in their learning, but there's a huge amount of variability in that. It really does vary from person to person quite substantially. One other thing we can do with these models is take the values that we're getting out of them on a trial by trial basis and try and link them to other things like visual attention. So I was really interested in visual attention because number one, attentional biases towards threat are really strongly implicated in anxiety disorders. The theory basically being that if you pay more attention towards more negative things in your environment at a visual level, that's going to influence your perception of the world to a greater extent. You're going to start thinking that the world is really scary and you're going to become anxious as a result. So I was quite interested to see whether we could link these learning processes to visual attention based on more kind of theoretical viewpoints, suggesting that attention and uncertainty should be linked. If you're more uncertain about something, you should probably pay more attention to it. So for me, it's an interesting opportunity to look at whether potentially you may be able to kind of generate an attentional bias towards threat based on uncertainty, or potentially based on just the general aversive value, i.e. how bad you're estimating something to be. When we did this, we found something kind of interesting, which was that uncertainty actually had no effect whatsoever on people's visual attention, which surprised me, still surprises me, to the extent that I spent weeks, I think, checking the code to make sure that I hadn't just messed something up somewhere. But yeah, if we look at the extent to which people's visual attention within this task is guided by how uncertain they are about the particular stimuli that they're looking at, no effect whatsoever. So that's the variance of this distribution, I should just clarify. However, we do see effects of other things. So for a start, which maybe is not surprising, we see effects of both the signed and unsigned prediction error. So if you receive an outcome, whether that's a shock or not a shock, you're going to pay more attention to the stimulus that has just given you that shock or has not given you a shock, depending on whether you're more surprised by that outcome. We also found a straightforward effect of the outcome itself. So when you get shocked, when you weren't expecting to, when you get shocked, regardless of whether you're expecting it or not, you're going to pay more attention to the stimulus that's just giving you a shock. And we also interestingly found an effect of the estimated value. So it's just how likely you think that stimulus is to give you a shock. And so I should mention also here, obviously, this is kind of where people are looking on the screen once they've been given an outcome. This, to me, this is kind of interesting because this does indicate that this learning process can influence your visual attention. Because we see this effect of estimated value, this is a kind of subjective estimate. It's not necessarily what's objectively happening in the task. It's just how bad you think that stimulus is going to be for you. The implication of this is that basically, if you're learning about things in a more negative way, you're going to think that you're more likely to be shocked. Therefore, you're going to pay more attention to that stimulus that you think is going to give you a shock. What this does kind of suggest is that you can create a sort of attentional bias towards threat via a bias in your learning. And so to me, at least, this may suggest that when we see a visual attentional bias towards threat, this may be kind of downstream from a bias in how you're learning about the world. if you're learning about things in a negative way, things are going to seem bad. You're going to pay more attention to those potentially bad things. Oh, I have arrows on here. I forgot about that. So overall, we can see that visual attention is influenced by a couple of things. Basically, how bad you think things are going to be, how bad things actually are when they happen, and also how surprising they are, but not by how uncertain you were about the outcome occurring, which is kind of interesting. The other thing we can do that's kind of I thought quite cool with this modeling approach is that we can then link the modeling itself to visual attention. We can plug the metrics of visual attention that we get back into the model itself. So what we're doing here is just taking our computational model that's fit purely based on behavior and looking at how well that explains people's visual attention. Instead, we can take the measures of visual attention and plug that into the model itself. And so there are a couple of hypotheses that we could come up with here. So what you could say is that if you're paying more attention to a stimulus when you receive an outcome, you're just going to boost the value of that stimulus. Somehow paying attention to it is going to make it more valuable. In this case, that means more valuable means more likely to give you a shock. Alternatively, you could say that paying more attention to it is going to make you learn faster from the outcome that you get. So because you're paying more attention to that stimulus, it might cause you to essentially kind of up your learning rates, essentially, for that stimulus that you're paying attention to. And these are things that we can just integrate into our computational model. We can either adjust the update rate parameters from our model based on the level of attention that we're getting from an eye tracking measure, or we can boost the value of the stimulus directly based on the measure of visual attention that we have. If we do that, what we see is that our model where attention influences learning, I think does slightly better than the model without any attention component in it at all, but does not do as well as the model where visual attention just boosts the aversive value of a stimulus. To me, this was somewhat surprising because I kind of would have thought that paying more attention to a stimulus would make you learn faster about it, but wouldn't necessarily just affect the value of it directly. But that's not what we see. Apparently, if you're just looking at a stimulus more, you think the stimulus is worse. I still don't fully understand why that is, but it's an interesting effect nonetheless. And it does demonstrate that these learning and attentional processes really do interact bidirectionally. The way in which you learn makes you pay attention in a different way. The way in which you pay attention makes you learn in a different way. We can also look at individual differences in the level of interaction between attention and learning. And so we get a parameter out of this version of the model that determines the extent to which visual attention is impacting upon learning, or upon the value of the stimulus at least. This theta parameter here. If we look at that across individuals, again, there's a fair amount of variability. This is not something that's really consistent across people. People do tend to vary quite a lot in the extent to which visual attention influences their learning. Okay, so for me, that was an interesting project because to me, at least, it seemed like maybe we could understand a little bit about how negative attentional biases are formed based on learning, and also tells us a little bit about how people track uncertainty using these kind of computational modeling approaches, and also tells us a little bit about how visual attention and learning kind of interact with each other. I felt quite happy with that because we got quite a lot of interesting results out of it, both for the kind of mental health side of things and also in terms of more basic insights into how people learn about uncertainty and how that uncertainty interacts with visual attention. The one thing we didn't learn is exactly how these learning processes relate to symptoms of mental health problems, which was the question that I'd initially started with. The problem was really that this was just a bit hard to do. It obviously makes sense that these aversive learning processes might be relevant for anxiety. It wasn't a question of whether we should do this, but it's very hard to actually do this in practice. And so what I did was turned to video games. The reason for this being that really most of these kind of mental health and behavior interactions that we're observing in a lot of these computational studies that you may have seen are very small. These relationships are often tiny and you need hundreds of people to be able to detect them. In this previous study, I think we had something like 65 people, which is fine. We did actually find some relationships with trait anxiety, but they're very small. Ideally, you need a big sample. The problem with that is that bringing hundreds of people into the lab is extremely time consuming. And this is really an area where online research has become extremely helpful. at least in the non-aversive domain. However, when you turn to the aversive domain, we can't shock people over the internet. And so we had this kind of conundrum. We want to be able to do hundreds of people easily online, but we also want to do aversive learning. How can we reconcile those things? My solution was to turn to video games because they can make people feel anxious without the need for things like electric shocks. I'll note that other people have done really ingenious things by playing aversive sounds over headphones across the internet, which does seem to work as well. Although you have the problem then that you need to make sure that people are actually listening to things and have their sound turned up, but still works very well as well. So can we create a video game that actually allows us to measure aversive learning? My argument was yes, we can. And to do this, I created a game that I just very simply refer to as the spaceship game because I'm apparently very unimaginative. Your goal here is basically to fly a spaceship through space while avoiding getting hit by asteroids. The interesting thing about this is that the asteroids occur in particular locations. You can learn where those locations are. This turns it into essentially an aversive learning task. So on the screen, we actually have two different safety zones. So asteroids will always appear in the middle, and then probabilistically, they can appear in the top zone and or not and, but or the bottom zone. And this means that you can learn how safe the top zone is, and you can learn how safe the bottom zone is. This is just equivalent to what we had in the previous task, where we had two stimuli that had a certain probability of giving you a shock. Here, you have essentially two stimuli that have a certain probability of producing asteroids that you can crash into, and you lose health. Eventually, if you lose enough health, it's game over. It's not properly game over, but it's game paused and you restart, and people find it quite unpleasant. And so it becomes just a very standard aversive learning task as far as when you're actually analyzing the data, even though to participants, it looks slightly more interesting and it's a lot more fun than a standard learning task, and they don't get shocked, which is quite nice. If we ask people to rate how anxious the game makes them feel, we do have a fair number of people who rate 0, but there's also a lot of people who actually rate it as very anxiety-inducing, which funnily enough, actually corresponds with at least my personal experience of giving people electric shocks. You have some people who don't really care about the electric shocks, and then most people do care about them to some extent. So to me, this is kind of reassuring. It's at least, I think, as valid as things we do in the lab with shocks. If we ask people how much they want to avoid getting hit by the asteroids, people generally rate that very highly as well. And if we kind of think about technically how we define something as being aversive, it's something that makes you feel anxious and something that you want to avoid. And so I think in general, we managed to hit those two criteria here, despite it being just an online video game. The nice thing about it being a basic aversive learning task at heart is that we can fit exactly the same kind of computational models to this task as we did to the previous task. We can use these beta learning models in the same way, and therefore we get our standard kind of estimates of shock probability, or in this case, safety probability, because I decided to flip things around, and the variance of that distribution as well. So we get a measure of both how likely people think things are to happen and how uncertain they are as well. We also get these different parameters that tell us about whether there are biases in people's learning, just as we did in the previous study. The benefit of this, though, is that we can do it in vast samples. It's funny, like 400 people when I did this seemed like a lot of people, and now 400 actually doesn't seem like that many people, but still a lot more than we would do in a lab. If we do this, what we can see is that a particular kind of subdimension of anxiety is linked to a bias in how people learn. So if we focus on how we can sort of characterize anxiety in terms of its subdimensions, we basically can divide it into cognitive and somatic anxiety. And this is what a kind of well-used scale for anxiety does, which is the STIXA, which I can't remember what it stands for, but state, trait, inventory of cognitive and somatic anxiety, that's what it stands for. But we use that measure, it splits it into these two domains, and so we can look at the extent to which those two domains are differentially or potentially similarly related to behavior. Cognitive anxiety is more about kind of symptoms of worry. Somatic anxiety is more this kind of physiological feeling of sweaty hands, just feeling kind of on edge. But what we found is that cognitive anxiety was really linked to this negative bias in learning. So people tended to learn more about aversive outcomes, i.e. getting an asteroid and less about safe outcomes, i.e. being safe from the asteroids. In addition to that, they tend to be more uncertain. So if you take the variance of those distributions that we're using within this model, that variance tends to be higher on average across the task for people higher in cognitive anxiety. So we have this picture where people higher in this dimension of anxiety are overall just kind of expecting things to be worse because they're learning in a more negative way, and they're more uncertain about their probability of being at risk as well. So I think this can kind of concords quite nicely with the symptoms of more cognitive anxiety. Interestingly, we found exactly the opposite pattern with somatic anxiety, which still confuses me. So basically, people higher in somatic anxiety tend to have a more positive bias in their learning and tend to be more certain about the outcomes they're going to receive, which I don't fully understand. Hopefully one day I will, but it's interesting nonetheless, I think. More things coming in. We could also do things that are a little bit more complicated. I won't spend a lot of time on this, but just to say, we can try and capture kind of more broad dimensions of symptoms and link them to people's behavior in the task. To do this, we used partial least squares regression. And what that means is that you can take a load of behavioral measures, i.e. the model parameters, etc., that we get from people's behavior, and a load of symptom measures, basically all these measures that we have from various different scales, and try and identify dimensions that explain variability across those two levels of data that we have. If we do that, we get two dimensions, one of which basically links kind of feelings of intolerance to uncertainty, more cognitive anxiety symptoms, depressive symptoms, to this negative bias and heightened level of uncertainty. So it seems like there is this kind of behavioral symptom dimension whereby people have this more negative bias in learning, tend to be more uncertain, and at the symptom level tend to experience more symptoms of anxiety, more uncertainty-related symptoms, and more symptoms of depression. Okay, the last thing I'm going to talk about is something a little bit newer. This may be very brief, potentially, we'll see, because it's all very new. What I've looked at so far is how people are learning about aversive value in general and how people track uncertainty about that aversive value. But in reality, we don't just need to learn about value. In fact, many decisions that we're making every day are decisions that we make in a so-called model-based way. What this means is that we're not just learning in a completely model-free way about the value of different options based on our kind of trial and error experience with them, but we're using an internal model of the world that we maintain in our brains somewhere to try and estimate the best course of action at a given time, combining value that we've learned about different states or actions in the world with this internal model of how those states and actions interact or relate to each other. So one question that I was really curious about is how we actually learn these internal models, and particularly whether people learn these in a similar way to learning value, and whether they track uncertainty about these world models. So, as I've shown in this previous kind of work, we can build computational models of aversive learning where people track uncertainty by building approximate beta distributions over outcome probabilities. And I was kind of curious to see whether we could use the same approach and apply it to world model learning. So we might assume that people are learning the structure of the world around them in a kind of similar way to how they're learning about value. You know, if I experience that going from state A leads me to state B, I'm going to think it's quite likely that I'll get to state B when I'm in state A next time, and so on. Again, we turn to video games because at this point, it's just a lot more fun. Once you start doing research with more video game-like tasks, you realize that everything else seems a bit boring. And like when I do this on Prolific, I often now get people message me saying, "Oh, that was so fun. I want to do this again. I wish everything was like this." And then I kind of don't want to go back to doing things that aren't video games. Yeah, we wanted to tackle this question of how people learn about a model of the world. And so we developed a game where people had to do exactly this. We very much adapted this from work from Claire Gillen's lab. This paper, actually, I should say 2024, because I think they published this year. No, maybe it was last year. I don't know. Anyway, very recent paper from Claire Gillen's lab, where they developed what they refer to as the cannon blast task, which is a essentially gamified version of the two-step task that was originally developed by Nathaniel Dorr. We just kind of flip things around a little bit to look at how people learn a model of the world. For those of you who are not familiar with the two-step task, it's a measure of the extent to which people are using model-based versus model-free decision-making. People are told essentially what the model of the task is, and have to use that model to try and figure out the best course of action on a given trial, given knowledge or given what they're learning about values at some more distal states. So in that task, people are learning the value of some terminal states that they have to get to, but they're given the task model that allows them to make model-based decisions to get them to those final states. What we do here instead is that we tell people the value of those final states, but we ask them to learn the world model. So it's just taking the two-step task and flipping on its head. So the way this is set up is you're firing this cannon at this little alien who's flying around space, and you have two options in terms of selecting cannonballs to fire at this alien. There is one on the left of the cannon and there's one on the right of the cannon. Each of these options has a different probability of giving you either a pink cannonball or a purple cannonball. And the pink and purple cannonballs have different chances of exploding before they reach the target. So ideally, you want to find cannonballs that are not going to explode. You want them to reach the target without exploding. What we do is we tell people the chance of the pink and purple cannonballs exploding. That's shown on the bars at the top. So the more full the bar is, the better the ball is. Essentially, the less full the bar is, the worse the ball is. But we don't tell people how likely they are to get pink and purple cannonballs from these two options. So what this means is that they're shown the actual value of those balls, i.e. the sort of terminal states in effect, but they're not told the probability of getting those balls. They're not told the world model. And so that's what they have to learn here. You have to learn probability of getting pink and purple balls based on choosing left and right options. It's very simplistic, it's a very simple model, but it is still a model of the task. And so learning which side predicts which color ball is what you need to do if you're going to be successful within the task. The way we structure the task is everything is quite changeable. The top figure here shows the probability of the pink and purple balls exploding. And this changes very rapidly. Because people are shown this, it's not something people are learning. It doesn't really matter that it's changing extremely fast because people are shown it all the time, so they don't really need to keep track of it within their head. So that changes every 4 or 5 trials just to kind of keep things interesting. The probability of getting different color balls changes a bit more gradually according to a random walk over the course of the task. And so this is what people are actually having to learn. This changes a little bit slower so that people can actually keep track of it. However, it does still change enough that people have to learn continually. They can't just kind of estimate it based on the first 20 trials or so and then relax. They have to keep estimating as the task goes on. We also have periods that we refer to as broken trials here, where the colors are not shown. And this is kind of useful because it basically heightens people's uncertainty. If you've not seen anything about the colors that you're getting for a few trials, you're going to become more uncertain about the probability of getting pink and purple balls because you've just not received any information in quite a while. So the other thing that we do to try and, I guess, kind of validate, well, number one, validate the modeling approach, and number two, just out of interest to see how these things relate to one another, is we ask people for kind of implicit confidence ratings. So on these trials, we give people this array of asteroids and ask them to shoot at them. And if the color ball that they get from the option that they've chosen matches the color of the asteroid, they win the amount of points that's shown on the asteroid. If it doesn't match, then they lose that amount of points. So what this means is that if I'm, for example, really confident that I'm going to get a purple ball, I should aim at one of the higher valued purple asteroids. If I'm not very confident at all, I should aim somewhere towards the center because I don't want to risk losing that amount of points. So this serves as a kind of implicit confidence rating. Basically, people are kind of betting on whether they're going to get pink or purple balls. This means that we can take the modeling approach that we use with people's behavior and look at whether the uncertainty measures we get out of that modeling approach relates to people's actual confidence ratings. That's a nice kind of check to make sure that what we're getting from a behavioral level actually maps onto something that people themselves are kind of reporting, if implicitly. If we do this, what we find is that that's what what happens. So basically, people's confidence ratings are related to uncertainty. But we can go a bit further than that. We can look at different types of uncertainty. And so we have two different types of uncertainty that we get out of our models. Again, we're using the same kind of beta modeling approach as we did in the previous studies. So we have this beta distribution over the probability of a particular outcome. In this case, though, it's the probability of getting a pink or purple ball. So it's the kind of structure of the task rather than a value exactly. So we have two measures of uncertainty. We have irreducible uncertainty, which is just basically how far away or how close, I guess, the probability is to 0.5. If it's 0.5, then you are maximally irreducibly uncertain, i.e., you're going to you have no idea whatsoever really what outcome you're going to get on a given trial. If it's closer to 0 or 1, then you're less irreducibly uncertain because you're pretty certain, pretty sure that you're going to get either a pink or purple ball. However, we also have reducible uncertainty, which is the variance of this distribution that we talked about before. So that is essentially the kind of width of this distribution. And that is reducible because that will reduce the more evidence you gain during the task. And as you play the task more and more, this will kind of get more and more precise. And so this level of uncertainty will reduce. The irreducible uncertainty will not. And if we look at the extent to which these different types of uncertainty predict people's implicit confidence ratings, both of them do. So essentially, the more uncertain you are in both senses, the less confident you are, which I think is kind of interesting. I think there's one other study that showed this a while ago. I can never remember the reference for it. But so this is not necessarily a novel finding, but it's nice to show it in this kind of task. Your kind of more subjective, I guess, uncertainty is formed of these two different types of more kind of objective uncertainty, I guess, that we can derive based on your behavior. And again, this kind of validates the modeling approach. These uncertainty metrics that we're getting from modeling behavior are not just coming out of nowhere. They're not just sort of nice measures that aren't actually related to anything subjective. They do indeed seem to be related to what people are reporting. We did this across two different samples with lots of people, and this seems fairly robust. The other thing we wanted to do is look at the extent to which these learning processes map onto different symptom dimensions. One thing that has been shown quite a lot, particularly by work from Claire Gillen, is that people who hire in sort of compulsivity and intrusive thought, this kind of transdiagnostic dimension that's quite linked to symptoms of OCD, tends to behave in a less model-based manner. And so one reason why that may occur is that they're essentially building a less certain model of the world. And so what I'd expect to see if that is the case is that people who are higher in that symptom dimension tend to be more uncertain about the world model they're building. And that's exactly what we see here. So this symptom dimension is the one in the middle, which is labeled compul, but it's compulsivity and intrusive thought. If we take the variance of the beta distribution over these transition probabilities, it tends to be higher in people higher in that symptom dimension. Conversely, which was a bit unexpected, it seems to be lower in people higher in anxiety and depression, i.e. they seem to be more certain about the structure of the world that they're learning. We can pin this down to ultimately kind of slower learning. I don't know why that arrow is there. That probably should, oh no, that does make sense. Anyway, sorry, confusing myself with arrows. Essentially, this level of uncertainty kind of comes down to the way in which people are learning. So if you're learning more slowly from these outcomes, you are going to be less certain because it's taking you a lot longer to accumulate evidence. Conversely, if you are learning a lot faster from different outcomes you receive in the task, you'll be more certain because you're building evidence more and more quickly. And so what we found is that people higher in this compulsivity, intrusive thoughts, symptom dimension tend to be learning slower, and then potentially as a result, they are becoming less certain. Again, this replicates across the two samples that we have, and so also seems fairly robust. What does this mean? My suspicion is that potentially this link that we're seeing between compulsive symptoms and less kind of model-based behavior may actually be explained by this process of world model learning. If you're less certain about the world model that you're using, you're probably going to use it less. So to summarize, we can use computational modeling to learn quite a lot about how people learn about the world and use this knowledge to make decisions. And many of these processes do seem to demonstrate links with anxiety, and also, as we saw in the last study, other symptoms like compulsivity. And so I really do think that uncertainty is a key factor across different dimensions of mental health. Although, as I keep realizing, it's quite complicated to actually understand, measure, model, etc. But hopefully, some of the work I've shown here gives some kind of clues as to how we can do this in a sort of replicable, quantifiable way. So I'll leave it there and just say thank you again for listening.
Thank you very much, Toby, for your very impressive talk, impressive research, and also very substantial research.
Thank you.
Yeah, yeah. I do have some a couple of questions or clarifications.
Yeah.
But before me, I will let others to ask their questions or clarifications. So anyone has any questions or clarifications, well, just speak out or type your questions at the chat box. Okay, I guess they need some time to prepare. I will start mine. So first, I want to ask a clarification. So based on the beta learning model, you found that the learning is the aversive learning is driven by uncertainty. But then you have another model that you found that the learning is driven by value instead of and surprise instead of the uncertainty. So I'm kind of confused. Do you have two types of model families, or am I miss something?
You're not wrong to be confused. I'm also confused. I don't know if I can go back to that.
Yeah,
So
yeah.
basically, they're two different analyses. So what we kind of find, I guess, if we look at the model fitting, the model that wins is a model where learning is driven by uncertainty. So in this case, yeah, I mean, not driven by uncertainty, but the rate at which you're learning is kind of dependent upon uncertainty. To clarify that a little bit more, the way in which these beta models work is that in effect your kind of learning rate is dependent upon uncertainty. We have a parameter that determines the rate to which you're updating on every trial, but that's also still dependent on uncertainty. So if I go back to, so I'll go back very far now. If I go back to this initial example, we might have a bias in the extent to which you're accumulating evidence on every trial, but relatively speaking, the evidence you're accumulating is less when you've already accumulated a lot than when you've not accumulated a lot. So, for example, here, this safety outcome here is everything you have. It's that is everything. You should pay a lot of attention to it. Whereas on this trial here, this kind of shock outcome that's number 10 of 10 is relatively little. Sorry, tells you relatively little compared to everything you've seen so far. What this means is that the more evidence you've accumulated, the less fast you're learning, i.e., the more certain you are, the less fast you're learning. And so learning within these models is highly dependent upon uncertainty just by virtue of that fact. There's no kind of parameter that determines how much influence there is on uncertainty, but it's just kind of implicit within the model that learning depends on uncertainty. Now, to kind of properly answer your question, what we're then looking at later is the extent to which this learning process impacts upon visual attention. And so in that case, what we're seeing is that visual attention is influenced by all these things, but not by uncertainty. Now, visual attention isn't necessarily learning. And so it may be that these things just simply diverge in this respect. So the information that you're taking in and using to update your estimates is impacted by uncertainty, but your visual attention while you're doing that, what you're looking at, is not impacted by uncertainty. That's still kind of surprising to me. So it's a bit weird, but yeah, I think that's how it's explained. These things just diverge a little bit.
Yeah, now I got you. So for the second situation, the dependent variable is the visual attention.
Yeah, exactly.
Okay.
Yeah.
Okay, yeah, I got it. Thanks for your clarification. And I would say so the model fitting results from my team also confirm the results from your team. So it's a cross-lab confirmation because before we conducted a couple of Pavlovian conditioning experiments, you have the CS plus, CS minus, and we also played a round of different models. You have the risk scorer, those Pierce Hall models, and prediction models, and finally, I would say also a beta learning models. And we found that the beta learning models is indeed the winning model in R. Yeah.
That's good to know. I know Dominic had a paper years ago where I can't remember what the model was exactly, but it was some sort of Bayesian model that also won in an aversive learning task. So yeah, that's good to know. It does seem like it's a fairly replicable result. Yeah, it's interesting. I don't know entirely why it is, but it's curious.
Yeah. But anyway, it's just a cross-lab confirmation for this robust of this beta learning models.
That's really nice. I'm glad to hear that.
Yeah. Okay, and then I also what I think is interesting is that you found the more people pay attention to a stimulus or items, the more people don't like this item.
Yeah.
And you think, yeah, I think this gives me a very plausible explanation for a learning phenomenon, the latent inhibition. So let's say if you pre-exposure to certain items at the initial phase, and then in the second phase, you ask people to associate this item with an aversive outcome, and usually people will have a slower learning rate. And I think your results provide a very convincing explanations because people don't like these items. So, well, that's why they probably have a kind of slower learning rate for these items.
Yeah, that's an interesting idea, actually. I don't really thought about that. Yeah, I mean, I think that makes sense. To me, yeah, it's still a little bit surprising because I would have thought that your attention would influence the actual learning process itself rather than just directly boosting value of things. But I feel like there is also work on the reward domain showing a similar sort of pattern as well. I could be wrong about that, but I'm fairly sure there is some work looking at that and showing that just paying attention to something does boost its value. Um, but yeah, that's an interesting idea actually, which I not thought about. So thank you.
You're welcome. Also, thank you for your implications. So I think I might have two more questions. So first is regarding the visual attention research. So if I remember correctly, you have a pre-outcome phase in which you measure how the learning affect attention, and then you have an outcome phase in which you measure how attention affected learning. So what I'm confused is that for this outcome phase, what do you think this outcome phase measures the influence of attention on learning instead of the other way around?
Um, well, so I think it measures both. I think we get both out of it, and that's kind of what we see in the results. So I mean, the slide that's up right now, so that shows the influence of learning on attention at the outcome phase. We, as you mentioned, we also get effects at the pre-outcome phase as well. But if we're really thinking about the learning process itself, that's kind of more post-outcome. So yeah, we do get effects of learning on attention within that outcome phase. But we also, as I showed, we also see the effects of attention on learning at that outcome phase as well. I think kind of what's happening is that when you receive the outcome, there are kind of two things happening that interact with each other. As soon as the outcome appears, based on things like how surprising it was, how bad it was, etc., your attention is directed towards it or away from it. As a result, potentially, that then also kind of feeds back into the learning process. And so you have, to an extent, this kind of circular process whereby if something is worse, you're going to pay more attention to it. But also, if you're paying more attention to it, you're going to think it's worse, which is kind of a bit confusing and interesting. But yeah, I think that all occurs at that outcome phase, exactly when you're receiving that outcome and where that's then influencing your own kind of estimates of what's about to happen next time around.
So I think it's also kind of difficult to disentangle this direction between attention and learning.
Oh yeah, I mean, I think it's one area where this kind of modeling approach comes in handy because by doing this on a trial by trial basis, you can see, the way in which you're paying attention on trial one influences the way in which you learn on trial two. So, based on kind of the order of effects, that causal direction can only go in one way really. But yeah, it's complex because yeah, as I said, you get these kind of feedback effects, and I don't fully understand how exactly all this fits together, but it's complicated.
Okay, but anyway, I was impressed by your use of this it's hierarchical Gaussian model, right? To model this time series.
So
Data.
yes, well, so it's hierarchical Bayesian modeling. So all of the well, are you talking about how we look at how the behavioral results influence the attention results?
Yeah, I'm talking. Yeah, exactly.
So we build hierarchical Bayesian regression models, which are really nice because they're kind of multi-level models essentially, but they have this kind of shrinkage effect whereby the sort of subject level parameters are kind of refined, I guess, based on the group level estimates. And so you kind of pull everyone's data together, you get better estimates at the individual level, and you can account for all the information you have at the trial level and at the subject level. So yeah, I love that approach and use it all the time.
Yeah, fantastic. I also use PyMC once, but then yeah, I think PyMC and Stan, they give us
Yeah.
very robust estimates.
Oh yeah, absolutely. Yes. I mean, it doesn't really matter what you use; they all work. It's more a matter of personal preference, I guess.
Yeah. Yeah, so I guess that's all of my questions or clarifications. Does anyone has any questions or clarifications? Just feel free to ask.
Hey, Toby, I have a question. Not really a question. So just for this slide, the uncertainty is not linked to visual attention. The result is you said it's like surprising, but it reminds me of a paper last year that's showing the pupil size equals uncertainty during learning. I think maybe there are complementary mechanism supporting learning.
That's a good point. So you're suggesting that maybe it's not actually where you're paying attention so much as the pupil size that we should be looking at.
Yeah.
That makes a lot of sense, I think. I think that the other thing is that there's this kind of confusion in terms within these literatures whereby within the sort of RL literature, people use attention to basically mean learning rate. And so based on that, attention and learning should be the same thing, but here we're looking at visual attention, which is a different thing, even though it's called attention. And so it's kind of surprising, but maybe it's just surprising because they're the same words when actually they're not the same phenomenon.
Oh, yeah.
That's a really good point, and I never looked at pupil diameter in this. I'm not sure why. I think I don't know, ran out of will. I'm not sure.
Yeah. And thank you for your great talk and your fancy slides, as always.
Thank you for listening.
Any more questions? Okay, all right. Then, Toby, thank you very much again for your fantastic talk, and also anyone else, thank you very much again for your joining. Um, I guess I'll just wish you a nice evening, a nice day.
Thank you very much.
Yeah, thank you very much.
Thank you.
Bye.